In 8.1, we look at an overview of different integration rules. We've gone in and we've looked at how to integrate a variety of things. We started out integrating things raised to a power. We've looked at integrating trig functions. We've looked at integrating e to the u, du over u, which integrates into natural log. We looked at how do you integrate things involving a squareds plus or minus u squareds, or u squareds plus or minus a squared. Some of those have square roots, some don't. Um, we looked at hyperbolics, how to integrate those, um, things integrated into inverse hyperbolics. So a pretty wide variety of things. So it's not always just immediately obvious when looking at an integral of which one of the formulas we're going to try to make it fit. So let's just go through a variety and look to see, okay, what are some things we can look for? So they give us a list on page 511 of various techniques that we can use to make things fit, integration formulas if they don't immediately fit. One, if we have something raised to a power, if the inside part is not u, it might be that we just need to multiply that out. Sometimes if we have multiple terms on top, we might need to break it into separate fractions, one term over the denominator, another term over the denominator, and integrate them separately. Square roots on bottom, if what's under the radical won't work for our u, then we might have to complete the square so that we have some form of a squared and u squared. If we have something that's not a proper fraction where the degree on top and bottom are either the same or the degree on top is larger, remember we divide that out using long division so that we have terms that are not improper, and then we deal with them separately. Occasionally, we might be missing something on top, missing a term, could be a constant, could be a variable, and sometimes we might have to add that number and subtract it. For example, if we let this denominator be u, then du would be 2x plus 2 dx. Well, we've got a 2x, but we need a 2, so we can add 2, but we would also have to take it away. So if we take the first 2 and put over our denominator, the last one put over our denominator, gives us something that will integrate. And we looked at one example back in chapter 5 of adding something and taking it away. One of our homework problems dealt with that. Sometimes we might have to use a trig identity to integrate something. We might not directly know how do you integrate cotangent squared, but we have a formula for integrating cosecant squared and 1, so we can use an identity to replace something with something that's equivalent to it. And one other thing to be on the lookout for, if we have a 1 plus sine, a 1 plus cosine, things of that nature, maybe 1 plus secant, 1 minus secant, then occasionally we might multiply top and bottom by the conjugate of that. Notice in this case, if we multiply top and bottom by 1 minus sine, 1 plus sine times 1 minus sine will give us 1 minus sine squared. There's an identity for that. 1 minus sine squared and cosine squared are the same. And that gives us something we can end up integrating. On this case, you could divide both terms by cosine squared. 1 over cosine squared is secant squared. That's something we can integrate. Here, sine over cosine squared, if you were to let u be cosine, then du would be minus sine x dx. So we basically have u squared on bottom, du on top. So that's something that we could also integrate. So we're just going to go through a variety of problems. We're going practice integrating these, look at using some of these different techniques. So let's go back to the problem here at hand. This one, notice the degree on top is 1 degree less than that on bottom. So let's just try, what if u were to be t squared plus t minus 4? Then du would be 2t plus 1 dt. So all of that is du. On bottom we have u, so that's basically the integral of du over u, which is integrates into natural log absolute value of u. If we look at the integral of 2 over 2t minus 1 squared plus 4 dt, if we let the whole denominator be u, that's not going to quite work out for us. But notice if we let what's in parentheses be u, then essentially we have a u squared plus an a squared on bottom. So let's see if we've got du. Du would be 2 dt, so that's du. So we have du over u squared plus a squared, which is one of our integration formulas. I believe that's arctan. So let's look at another. Let's look at integrating 3x over x plus 4 dx. So the first thing that jumps out is the degree on top and bottom are the same, so this is an improper fraction, so we need to divide that out. So we're going to take 3x divided by x plus 4. So x goes into 3x 3 times. 3 times x is 3x. 3 times 4 is 12. We're subtracting, so do the opposite sign, so 3x minus 3x is 0. 0 minus 12 is minus 12, so that's our remainder. We do that over our divisor. So this is essentially 3 minus 12 over x plus 4 dx. So if we want to integrate that, the first term is just a constant. This second one, that integrates as natural log. Notice if we want to integrate 12 over x plus 4, 12 comes out front. The numerator is just the derivative of the denominator, so that integrates into natural log absolute value of u. So improper fraction, make sure we divide that out. Let's see, let's take a look at x times 3 plus 2 over x squared dx. So if we just let what was in parentheses be u, u is basically 3 plus 2x to the negative 1 power. So if we try to find du, we get 0 minus 2x to the negative 2. So remember, bring our exponent down, x to the 1 less power dx. Well, that's not what we have outside, so maybe picking that is not the right choice. Remember, one of our options was that if we have something raised to a power and what's inside won't make u and du, then one alternative is to expand that. So we have an x out front. If we square that, we could either write it twice and distribute, or the shortcut for squaring a binomial is to square the first. Take the product of these and double it, so 3 times 2, that's 6 over x, so double that, and you get 12 over x. The second one squared is 2 squared over x squared. Distribute the x times 9, x times 12 over x, so the x's cancel. X times 4 over x squared. So x on top and x on bottom cancel. So all of those integrate. This is just the power rule. X to the 1 greater power over that power. This one you pick up your variable. And this is just natural log, du over u. Let's see. About cosecant squared x e to the cotangent x dx. So let's think. If we were to let u be cosecant squared, what's the derivative of that? Well, that would be messy. We would have to use a chain rule. The derivative of the outside is bring down our exponent, cosecant to the 1 less power, times the derivative of the inside. The derivative of cosecant, what's that? Negative cosecant cotangent, which looks nothing like what we have over here. So letting u be the cosecant squared part won't work. You do notice we have e to a power. And that's the only place we have an e. So if we don't have e's other places, then it's generally a good choice to let your exponent of e be u, because we know how to integrate e to the u. So let's see if we can make that into e to the u. So if u is cotangent, remember that the derivative of cotangent is negative cosecant squared dx. So we've got our cosecant squared dx. We just need a negative. If we multiply by a negative inside, then we have to do that outside. So that's du. This is e to the u, so we just have negative the integral of e to the u du, which of course e to the u integrates into the e to the u, so minus e to the cotangent x plus c. Let's see, what else? Let's take a look at this one. Let's look at 2 over 7 e to the x plus 4 dx. So a couple different things we could try. We could look at this as maybe u squared plus a squared, but this is not really being squared. This is not a perfect square, which doesn't necessarily have to be. So before we try a u squared and an a squared, let's just, in general, let the denominator be u and see what happens. So if we let the denominator be u, then the derivative of that would be 7 e to the x dx. The derivative of e to the x is e to the x. So let's think about this. Let's see if we can make that. So this doesn't look to work. So let's just see what we can do. Let's bring the 2 out front. We need a 7 e to the x to complete that, but if we put one of those on top, we have to put one on bottom. So we have 2 integrate 7 e to the x dx, that's du. 7 e to the x plus 4, we call that u. But what is 7 e to the x? If we take this top expression, solve that for 7 e to the x, we subtract 4 from both sides, so that would be u minus 4. So we could call that either what it is or integrate du over u squared minus 4u. Now, unfortunately, that's not going to be very nice and neat. If we let the denominator be, instead of u, calling it v, then dv would be 2u minus 4. Well, we don't have that either, so something else we need to do. And back when we were doing du's over u's, if we came out with two factors on bottom, then we did partial fraction decomposition. We would rewrite that, and let's call that 1 over u minus 4 times u. We would break that up into two separate fractions, something over the first factor plus something over the second factor. And the way we would determine what a and b needed to be, we would get our common denominator for both of these fractions. So the first one is missing a u on top and bottom to have that common denominator. The second one is missing a u minus 4 on top and bottom to get our common denominator. Then if we combine those, we get a times u plus b times u minus 4 all over our common denominator, which, notice, our common denominator is the same thing as our original denominator. Since these denominators are the same, then the numerators have to be equal. So 1 in a times u plus b times u minus 4, those are equal. And we could solve that as a system of equations, but the way that we did that in pre-cal or when we were doing natural logs is we made a substitution. What would make this equal to 0? So if we let u be 4, we would have 4 times a. If we put a 4 in for u here, we would get b times 0, which is 0. So if we divide both sides by 4, we get a. Then if we let this be 0, that's what would make this term go away. So we would have 1 equals a times 0, or 0, b times 0 minus 4, so minus 4. So b is negative 1/4. So we can rewrite this. Let's see, a was 1/4. So 1/4 over u minus 4. B was minus 1/4, so minus 1/4 over u du. So we can pull a 1/4 out front for both of those. So if we bring a 1/4 out front, we already have a 2, so 1/2 the integral of 1 over u minus 4 minus 1 over u du. Both of these integrate into natural log. Notice if this is our denominator, the derivative of this is 1 du, so du over u. So that integrates into natural log, absolute value u minus 4. This is 1 du over u integrates into natural log, absolute value of u plus c. So now we just need to substitute back into our original variable. U minus 4, if we subtract, we saw earlier that u minus 4, that was 7e to the x. U, that was 7e to the x plus 4. So that was messy. That was very messy. but we started by picking something to be u. We saw what we were missing for our du, and traditionally, if we're off by a variable, we say, well, we can't really do anything about that, but technically we can multiply top and bottom by that same thing. So if we multiply top and bottom by 7e to the x, and then make our substitution, that's our du. We said that was u minus 4, that was u. While that's still messy, we've gotten rid of our function e to the x for the time being, so that we have something that's a little bit easier to deal with. And then keep in mind, if we have a product of factors on bottom and we can't do anything else, partial fraction decomposition, breaks those into two separate fractions, both of which are things we can integrate. Always remember that once you integrate, you put your final answer back in terms of your original variable, x. So u minus 4, that was 7e to the x. U was 7e to the x plus 4. All right, so that one was messy. That was one of the messiest ones we've done so far. But it was all in being careful with what we pick our u's to be. Let's do one more. Let's look at tangent x times natural log of cosine x dx. So there are a variety of things we could pick for u. Of course, letting u be just x, that doesn't really make much sense because that's just changing x to a different letter. X, u, that's all the same. So we could use tangent, we could use cosine, or we could let natural log of cosine. All of those are options of things that we could let u be. So let's start with the first one. If u is tangent, the derivative of tangent is secant squared. So this would be u that looks nothing like secant squared, so that one's not going to work. Let's see about this one. If u is cosine, the derivative of cosine is negative sine dx. So that would basically be natural log u, and then this doesn't really look like that. So that's we're off. We have a cosine. A cosine on bottom, and we can't just pull a cosine out front because that's a variable. So it doesn't look like that's going to work. So let's try this one. If u is natural log cosine x, then what's the derivative of that? So remember, the derivative of natural log, we put that u on bottom, the derivative of that on top. The derivative of cosine is minus sine and dx. Remember, recall that sine over cosine, that's tangent. So bring the negative up front. That's tangent x dx. So tangent x dx, if we had a negative with that, then all of that would be du. If I multiply the inside by negative, I need to multiply the outside by negative. So that tangent x dx, I'm going to call that du, and natural log x, natural log of cosine x, that was u. So as messy as that is, that's just u du, which u du integrates into u to the 1 greater power over that power plus c. So in this case, u is natural log of cosine x, all of that squared over 2 plus c. So that's our antiderivative of that. So I'll give you a variety of these. It's not always immediately obvious what you're going to do to begin with. The biggest thing is pick something, try it, and see what happens. Never know what you're going to end up with. Let's do one more example real quickly. Let's integrate 1 over cosine x minus 1 dx. If we let u be cosine x or cosine x minus 1, then du would be a negative sign. We don't really have a negative sign. If we tried to put that up here, the opposite down here, we would run into something messy, kind of like we did with the e to the x's. But recall that one of our options was if we have a 1 plus sine, 1 plus cosine, or a minus, then one option is to multiply by a conjugate on top and bottom to try to make it a Pythagorean identity. So let's multiply top and bottom by the conjugate of this, which would be cosine x plus 1. So on top, we have cosine x plus 1. If we distribute that, we'll get a cosine squared. We'll get a cosine x minus cosine x, which cancels, minus 1. And anytime we have a sine squared or cosine squared and a 1, think back to the Pythagorean identity. Sine squared plus cosine squared is 1. So we could do this different ways. We could solve this for cosine squared and then substitute, or we could rewrite this as cosine squared minus 1. Notice, subtract 1 from both sides, and we get sine squared plus cosine squared minus 1 is 0. Well, there's our cosine squared minus 1, so if we subtract sine squared from both sides, cosine squared x minus 1 equals the opposite of sine squared. So that gives us cosine x plus 1 on top, negative sine squared on bottom, or we could put sine squared and then put the negative out front. A couple different things we could do here. One thing we could do is we could write this as two separate terms. We could write this as cosine x over sine squared x plus 1 over sine squared x. Let's see. Well, that second one, 1 over sine, that's cosecant. So that's cosecant squared x. We could look at this one a couple different ways. We could pick one of the signs out, call this cosine x over sine x times 1 over sine x. Cosine over sine, that's cotangent x. 1 over sine, that's cosecant. We know how to integrate cosecant cotangent. Or we could let the denominator, let sine be u. If we let sine be u, then we have u squared on bottom. The derivative of sine is cosine, so du on top. So we would have du over u squared. So either one of those techniques is going to be okay. So if you don't recognize breaking it up that way, we can just leave it. If you want to, instead of calling that sine squared, we can call it sine x all squared. Let's go ahead and write this as two separate integrals. So it's minus all of this, so that applies to both. So minus the first one, minus the second one. So for the first one, we said if u is sine, du, the derivative of sine is cosine. So that first one is du on top, u squared on bottom, or u to the negative 2 du. U to a power that integrates to u to the one greater power over that power. The negatives cancel out, so that's 1 over u. So this integrates into 1 over u, where u is sine. So that takes care of the first one. The second one, whose derivative is cosecant squared? Well, let's see, the derivative of cotangent is negative cosecant squared. So that is negative cotangent plus c. So 1 over sine, that's cosecant, minus a negative, so plus cotangent plus c. So a little messy, but we took something that originally we didn't have an identity for. We didn't have anything that would be a good choice for u. So by multiplying top and bottom by the Pythagorean, or by the conjugate, so that we get something that's related to the Pythagorean identity, then we can make a substitution. We can divide that out, and that'll produce two integrals that both of those are things of which we can do. So these things are not things that are just immediately obvious on all of these. We essentially have to go back to our toolbox, think of, well, what are the different things that we could try? Try one of them, see what happens. Sometimes we get something that's really messy and it doesn't look like it's going to work, and we just stop and we try something else. Sometimes it immediately goes into something that we can integrate. Sometimes we might have to make a second substitution or a second change. But one of the biggest things is just try something and see what happens.